very much for the introduction. So my name is Pietro Dirix, and I'm currently pursuing my PhD at the Cardiovascular Magnetic Resonance Group from ETH and University of Zurich. So we are an imaging group focused in improving MRI techniques and also simulating and modeling various MRI strategies like perfusion imaging, motion and strain mapping, diffusion tensor imaging, and also blood flow quantification, which is going to be our topic of interest for today. And in particular, a technique called 4D flow MRI, which allows us to image 3D volumes per specific cardiac frame. And this allows us to visualize and see how patterns in the aorta change for flow, for example. So here you can see a healthy aorta. And of course, we know that pathologies in the aorta have a direct impact on the way the flow behaves in the aorta. So here you see another example with a stenotic dilated aorta. So there is an interest in being able to image and understand all these flow patterns in order to characterize diseases in the aorta. So today we will focus on the calcific aortic valve disease, which is a progressive disease which consists in calcification of the aortic leaflets, which will tend to stiffen them and avoid their complete motion and opening. So it's a progressive disease that can lead until valve obstruction here. Relatively prevalent among older adults, so about 10% of people above 80 years old have a diagnosed aortic stenosis, but it can also happen in younger adults if there are abnormal aortic valves in the patient. So my symptoms are relatively mild, but when severe symptoms appear, the rate of death drastically increases to about 50% after 2 years of first symptoms. So there is a fundamental importance in obviously understanding the disease, but also being able to predict its evolution and being able to time accurately medical interventions such as valve replacements. So we are interested in understanding what happens to the flow when there is an aortic stenosis. So here we have an idealized stenotic case where you can see the stenotic throat over here. And if we look at the pressure in this channel, we can see we start with a relatively high static pressure. We have a drop in pressure at the level of the aortic stenotic throat, and then we see a recovery of pressure further down the channel. But what happens here is that the drop in pressure, so the recovery over here, never reaches the initial value at the beginning of the channel before the stenosis. So this is an irreversible pressure loss, which is actually lost energy. And because the body needs the same amount of blood to function properly, actually the heart has to compensate for this pressure loss, and there is an extra stress onto the myocardial muscle. If we look now at the same plot but for velocity, we can see a drastic increase in velocity at the stenotic throat over here with corresponding increase in kinetic energy. And then we see this interesting region over here where the instantaneous velocities, depicted here in black, differ notably from the mean velocities here in yellow. So this is a turbulent region. We have velocity fluctuations, and then we relaminarize the flow further down the stenosis, and we see that there is no difference between instantaneous and mean velocities. Now, if we take a sample in this turbulent region and we measure the fluctuations in time, we can plot the variations in flow. And if we plot the density of these variations, we can see that they are quite well represented by a Gaussian distribution. So it becomes quite straightforward that we can represent this flow as a mean component and a fluctuating component. Now, if we take the covariance of this fluctuating component, we get what we typically call the Reynolds stress tensor in fluid dynamics. And it gives us an indication of how much fluctuation there is in the flow. If we take the diagonal of the Reynolds stress tensor, we get turbulent kinetic energy, which gives us an indication of how much energy there is in the fluctuating parts of the flow. And it's a fundamental indicator of turbulence we will use in the next slides. So if we plot turbulence in the same stenotic case, we can see there is no turbulent kinetic energy at the beginning where we have laminar flow. Then we get this rise of turbulent kinetic energy in the region where we have high fluctuations of flow, and then we relaminarize over here. Now, fluctuations, mean velocity, pressure, they are all linked in the flow. So it is fundamental to be able to image all the components of flow. So not only mean velocities, but also fluctuations. So how can we do that in MRI? So I will present here the fundamental equation we are using to describe the signal when we acquire flow. And I will describe this equation later on, but I will just present a typical image we get from MRI from 4D flow MRI. So it is a complex image, and if we look at the terms in the equation, we see that one of the terms, the phase term, actually is proportional to mean velocity, which means that from the phase of the image we acquire, we can reconstruct mean velocities. Similarly, if we look at the other term, we can see that there is a proportionality term on the magnitude of the image that depends on the Reynolds stress tensor we defined earlier, so it represents the fluctuations. We can also similarly reconstruct the fluctuations by looking at the magnitude of the image, and we get on one side estimation of fluctuations, and the other side estimation of mean velocities. Now, knowing these two values is fundamental, right? Because it allows us to do correct flow quantification. We can use it to do labeling, segmentation, to diagnose a pathology, and ultimately decide if an intervention is necessary or not. But in order to use these data efficiently in the medical domain, in the clinical setup, we need automatic processing tools. Now, one of the most promising options is using neural networks. But these have two fundamental limitations for us. And these are that we need large data sets in order to train the models, but more importantly, we need ground truth in order to train models. And the ground truth part is really difficult to obtain, right? So even if we were to have large data sets of 4D flow MRI, it is really difficult to estimate ground truth from manually having to segment or label these images. So we propose a pipeline to generate large data sets with paired ground truth data and MRI synthetic data. Now, if we look at the imaging pipeline in general, we have an analog object we want to image. It has some tissue properties, some blood properties, and then we have a transfer function that allows to go from this domain to a discrete image. Now, in our pipeline, we replace the real object by a synthetic object. So we developed an in-house segmentation tool and subsequent mesh generation tool in order to segment patient-specific aortic geometries. And we can use these geometries to run computational fluid dynamics to extract velocity fields and turbulence fields. Now, just to give a better idea of what we are doing here, we also took into account motion of the aorta in order to be really close, as close as we can be to reality. So you can see here the motion of the MRI slices we used to generate this model and the corresponding variation in area over here. Okay, now that we have this CFD model, we can use the signal equation we presented earlier in order to generate a synthetic MRI signal. We can also do operations in Fourier domain, like cropping to change the resolution or adding noise in order to make the images more realistic. And once we have the final signal, we can reconstruct the expected MRI velocities over here and the expected MRI Reynolds stress tensor. Now, this pipeline was validated, and it is currently under review. But just to give you an idea of how it compares to real clinical data, I just want to show you this image. So on the left side, you have our pipeline. And on the two right columns, you have two patient-specific data sets that were acquired with an MRI. And we see that our synthetic velocities and turbulence present features that are similar to what we would expect in real medical data. So we have some confidence that actually what we are generating is close to what we would obtain in reality. And this is important because that's the whole goal of what we want to do here. We want to be able to generate these ground truths using CFD in order to generate synthetic data sets that we can then use as a training set in order to train, for example, a network to perform some inference on hemodynamic parameters, such as peak velocity, pressure drop, or degree of severity of the stenosis. Now, I presented until here only patient-specific cases, but of course our objective is to extend this approach to a large variety of synthetic geometries. And for that, we are developing a synthetic generator of aortic shapes. So we used data available at the Hospital of Zurich, University Hospital of Zurich. And we performed some principal component analysis in order to estimate the modes in those geometries and the variations of those modes to generate this shape model we now have, and that allows us to generate random shapes that have a good representation of the geometry space of our array. And we can use all these synthetic geometries we're able to generate in order to run simulations and create a data set. But talking about simulations, so the simulations we presented until here require a lot of computational power. About 300 to 500 CPU hours per cardiac cycle for one of these simulations, which means that if our objective is to generate a large amount of synthetic data, let's say, for example, 100 geometries or that order, we also need at least 10 cardiac cycles per geometry in order to account for cycle-to-cycle variations in the flow. We also need time to do data curation, prepare the data. And finally, we also need that time to actually create the synthetic for the flow MRI data. So then we are more in the order of between 300 and 400,000 CPU hours in order to generate the synthetic data set. Now, from studies with the high-performance computing cluster of ETH, we determined that the optimal parallelization level is reached for our simulations with around 200 CPUs per geometry. And this is where actually cloud computing, and in particular Microsoft Azure, enters the picture. So it would allow us to do some massive computation in order to accelerate the process of synthetic generation and bring it down to realistic times in order to have a time frame that is achievable for realistic operations of this project. And this is where we are currently at. So we have a viable model to generate synthetic data, and we will perform this large study of a generation of various geometries in order to create this synthetic data set. Of course, the ultimate goal is to use that data set in order to train a network or algorithms in order to perform, like, for example, inference, as I suggested earlier. With that, I would like to conclude my presentation, and thank you very much for your attention. And of course, I thank also all the collaborators that are helping me out with this project. Thank you very much.
Thank you.